All right, everybody. Hello, hello. Welcome to Chapter 10 here. This is our 6th total unit that we've gotten up to so far, which is pretty wild. We're almost halfway through the school year in terms of content, which is pretty crazy. So here we go, Chapter 10, right? Like I was saying, I have been saying now for well over a month, a lot of Quarter 2's content is going to come from this holistic idea surrounding chemical bonding, right? And this is essentially going to be part 2 of that in Chapter 10 here, which is centered around covalent bonding, right? Last chapter in Chapter 5, last unit rather in Chapter 5, we spent a lot of time talking about ionic bonding. And so this chapter, in Chapter 10 here, we are changing gears and talking about the other kind of bonding that was very briefly mentioned at the very beginning of Chapter 5, okay, which is covalent bonding. Now, some of the big ticket items here with covalent bonding, right? If we remember way back, the definition of covalent bonding is the sharing of electrons between two or more non-metals, right? This is the big thing here. They have to be non-metals present here, right? Non-metals and non-metals only, right? So we're not talking anything to the left-hand side of that staircase, right? This is my really a horrible version of a staircase, right? Anything on the left-hand side here, no good, right? We're only talking about the stuff to the right of the staircase, right? So keep that in mind as we progress through talking about this stuff here, okay? Again, since this is not any kind of transferring of electrons like it is for ionic bonding and only a sharing of electrons, these covalent bonds do not form ions or charged particles, right? So the idea of an ion that we've been kind of drilling into our heads the last month or so, we kind of have to start to abandon that for a little bit. Okay, we're going to make our way back to it, so don't like totally abandon it, right? But we have to start thinking about covalent bonding as a sharing of electrons. And because of that reason, because there is no direct transfer of electrons from ion A to ion B, right, the positive to the negative ion, right, there is no ion that forms. We're just sharing electrons, okay? And because of that reason, because there is a sharing of electrons between the different atoms present in these covalent molecules, they form molecules instead of compounds. So there's ionic compounds and there are covalent molecules. All right, so molecules are formed when there's a sharing of electrons, not a transferring, a sharing, right? And this is an example right here of two hydrogen atoms with their one single valence electron, right? These are two Lewis structures of hydrogen atoms here. And these two Lewis structures, each on their own, have one single electron by themselves. But as soon as these two hydrogen atoms bond together, they're going to share those electrons with each other, right? So if we take a look at this hydrogen molecule on the right-hand side, first and foremost, we see the word molecule, which in our minds, we should be instantly thinking covalent molecules. And second here, notice how these two valence electrons are hanging out directly in between the two H's. That is indicative of a sharing of electrons. No more transferring at all, right? Just sharing and sharing only, okay? Now the octet rule, okay? Can't escape it, right? It's back in action here in covalent molecules. Neutral atoms form ionic or covalent bonds to satisfy the octet rule, right? So the idea of this octet rule, the rule of 8, still holds true in covalent bonding. The octet rule states that atoms tend to gain, lose, or share. And that's not where we are at, right? Sharing, right? Or share their valence electrons to achieve 8 electrons in their outermost energy level. Again, 8 equals octet. 8 is your favorite number of chemistry. And again, the reason why that's the case, the reason why pretty much every scenario of bonding always strives towards 8 valence electrons is because 8 means very stable and very unreactive. And that's always what systems in chemistry always try to shift towards. They shift towards stability and they shift towards unreactiveness, right? They want to be peaceful. They don't want to be reacting and be unstable, right? They want to be very stable and very unreactive. Now, continuing this idea of a molecule versus a compound, okay? Particles involving 2 or more atoms covalently bonded together is what a molecule is. And this whole thing right here, this little symbol with all these these C's and H's and these lines here, these are what covalent molecules look like. This is a very basic type of covalent molecule here. This actual molecule itself is actually called ethane, E-T-H-A-N-E, ethane. In a molecule, shared electrons orbit both atoms, right? In every single one of these instances here, these lines here, which I'm going to highlight and draw over in orange here, right? This line here, this one here, here, between these two C's, this H and this C, this H and this C, and this H and this C. All these orange lines I just overlapped with these originally black lines that were there. Okay, these are called single covalent bonds. And those of us that have, had their lab more recently with our covalent molecules lab, you guys would have drawn and essentially put together a bunch of these, right? Think of those wooden dowels that you sort of manipulated in lab the other day, right? Those wooden dowels were indicative of single covalent bonds. And it's a sharing of one pair, and when I say, and obviously use that word pair, we're thinking two electrons. So every single one of these every single one of these single covalent bonds here that I've, again, highlighted in orange over here, represent a sharing of two electrons between those specific atoms. And I'm going to go back here a second, okay? So looking at, let's say, for example, this H and this C here, okay? In between both of these two atoms here, this carbon and this hydrogen here, is one single covalent bond, which represents a sharing of two electrons present between those two. So that's representative of two electrons being transferred, or not being transferred, but shared between the two of them, right? So at any given time, that means that carbon has these two electrons associated with it, but so does this H here, so does this hydrogen. This hydrogen also at any given time can be essentially sharing these two electrons between the carbon and between the hydrogen, right? So they both essentially claim ownership over these two electrons at any given time. Okay, and that is what a single covalent bond is in this particular case. Now, moving on to how these covalent bonds form. Right, we kind of did something similar with the hydrogen example we had at the start of our lecture video today here, right? But here's another great example, right? Two fluorine atoms, right? These two fluorine atoms want to react with each other and form a covalent bond. Well, here is how it happens, right? Something that we are quite familiar with, right, are drawing Lewis structures for atoms, right? And this is exactly what we've got here. We've got a fluorine atom right here with another fluorine atom right here, and it has its 1, 2, 3, 4, 5, 6, 7, right? Different valence electrons. Because if we look at the configuration of fluorine here, which is 2-7, this 7 represents the number of valence electrons in an atom of fluorine. So both these atoms of fluorine have their 7, right? But again, the question remains, guys, as always, how many does it want? 8. Hopefully you said 8, or thought 8, right? 8 valence electrons is what it wants. So in order to do that, without transferring any electrons from any metals, right, we're only dealing with nonmetals here, without transferring electrons, it actually has the option to bond to another nonmetal, in this case it's the second fluorine atom here, and share its electrons, share its valence electrons. Well, specifically here, guys, it's going to share this valence electron, and it's going to share this valence electron. So essentially what happens is both of them sort of bond together, allowing each atom here to claim ownership of the other's valence electron, its 7th valence electron. So what happens here is that these electrons essentially form a single covalent bond here, where they now are both going to be essentially shared between both atoms of fluorine, right? So now in this case here, we can see these, get my eraser out here and kind of clear the way here. In this example here, we can see where my circles lie, right? So now that we have these two dots here, we've got a dot here and a dot here that represents, essentially a shared single covalent bond here. If we were to circle all of the electrons associated with this left-hand side fluorine here, we're going to say that it has 1, 2, 3, 4, 5, 6, 7, 8. 8 valence electrons, beautiful. That's exactly what it wants. Now let's change gears here and look at the fluorine on the right-hand side, because again, this is bonding and sharing these electrons. So even though this dot right here and this dot right here was also associated with our left-hand side fluorine atom, it's also, if we draw a circle around it, also associated with the fluorine on the right. So again, at any given time, it counts for both atoms in this molecule. These two electrons here are able to be counted for both atoms in the molecule. So if I count 1, 2, coming from the sharing, 3, 4, 5, 6, 7, and 8. And look at that. both fluorine atoms have exactly 8 valence electrons centered around them, 6 of them not being shared, 2 of them being shared, right? So accounting for a total of 8. All right, and again, that is essentially how covalent bonds are formed, right? Their electrons are shared between the two things that are essentially being bonded over, right? It's these two fluorine atoms, this fluorine atom and this fluorine atom bonding. So the electrons being shared are these 2 electrons here being shared amongst the 2 of them. Now, last thing I'm going to drop here on you guys before I end the video here is essentially going to be me setting the stage for when I see you guys next, okay? Drawing these Lewis structures, right? It's important to recognize how these covalent bonds form, but it's even more important to recognize how we actually go about drawing them to create Lewis structures of these molecules, right? Essentially, guys, we're going to be focusing how to achieve one of these guys here, right? How do I draw one of these guys here? That's essentially what we're going to be covering next class here. So in a quick roundabout way, if we take a look at some of the directions here, there's a lot going on here, but it's all centered around this very first set of 1, 2, 3, 4 steps here. First things first, write out the formula. Label the metals, the nonmetals, and the polyatomic ions if they are present. So that's always the first step. If you have a formula, you have to identify the pieces of the formula, whether they're metals or nonmetals or polyatomic ions. That's going to allow you to determine if the bonding you have present is covalent or ionic. If you are able to determine if you have covalent bonding present, because you've got nothing but nonmetals bonding to each other, you can move on to these next set of steps here, right? 3, 4, 5, and 6 in the first set here. So for covalent compounds, calculate the total number of valence electrons, and I'll show you how to do that next class. 4, identify the central atom and draw a skeletal structure. The central atom is oftentimes going to be the atom that there is only one of, or is the least electronegative, right? So 2 simple concepts, one of which we're familiar with, right? We hopefully all somewhat remember that word, electronegativity. The other one is you're just counting, right? So if I have a situation where I've got 1 carbon in 4 hydrogens, I only got 1 carbon, so that's the one I have the least of. That's going to be my central atom. 5, add electrons so that each atom only has 8 electrons. There is one catch here, however. If you are ever running into a situation where you are dealing with a Lewis structure that has hydrogen, helium, or boron present, those guys actually only require up to 2 valence electrons, and I'll show you why when we meet again in class next. Okay, so 2 as opposed to 8. Lastly, number 6, check total number of dots equals your total number of valence electrons. If not, add double or triple bonds until the number of dots equals the number of valence electrons. And yes, there are different types of bonds other than just single bonds. There are double and triple bonds, which again, those of us that have done the recent covalent molecules lab actually would have experienced that the other day. And again, this is where we're going to end things here. The rest of these instructions here are for ionic compounds, and there will be a little bit of review associated with these ionic compounds because again, we've already actually kind of touched on them already last chapter in chapter 5. So I'm not really going to allocate too much time to them both in this video as well as in class. Okay, so guys, I will see you next class. Take it easy.